Okay, everybody, I think I'm gonna go ahead and get started. Great to see all of you guys today. First, just want to start off by thanking you again for kind of putting up with last week. It was a little bit unusual, but my parents told me to tell you all thanks for letting me go over there and spend some extra days with them during that. I only had one day of class for like 11 straight days. It's like, okay, I think I can make this work in Zoom. I hope that it worked out okay and that most of the connection was good and all that kind of stuff. But yeah, I got back a couple of nights ago, and this is really just our 1 week back until we have another week off. So next week is the holidays for the fall break. So we just have to work hard for what, another 48 hours or so for this class, and then we'll be off on a little bit of a break. Quick reminder that we have an exam on Thursday. I have not written it yet. You won't be surprised about that. That's always a last minute thing with me. I did a study session for it last night, which was great. There were about half the class was there, I would say. I took a video of that session and I sent it out to you guys all, so check your email for that. I'm going to redo that session again tomorrow night. There's a few problems I didn't do in the first review. I'll do those tomorrow. By the way, it's at 7 o'clock. So Wednesday review session. I just wanted to pick a different time because yesterday I did it at 5. So tomorrow I'll do it at 7. So just trying to mix it up enough that maybe some different people could make it if they want to make it. Anyway, I'll start off with some of the new problems that I did not cover yesterday, and then I'll probably sort of recycle some of the questions that I had done yesterday. I'll come back and recycle those again. But I will record it and I will send it out. So if anybody isn't able to make it, but you're kind of wanting to see the session, you'll be able to do that. Sometime after 9 o'clock tomorrow night, there'll be an email coming out with that on it. Also, there is a homework assignment that's due tonight. And in a little bit, I'm going to ask you if you have any questions on it. Normally, I don't spend a lot of time in class going over homework, but because the exam is right around the corner, I want everybody getting this thing done. And so if people are stuck on stuff with this assignment, we should try and get it cleared up together. I'm happy to do that. So as far as today's class goes, we'll probably spend about half of it kind of just wrapping up this last homework and some of the ideas here right from the end of the material from chapter 12. And then I'm hoping to have a little bit of time to kind of start talking about a new topic that would not be part of Thursday's exam, just to get kind of a little bit of a springboard launch into it. But we'll see how much time we have. Okay, does that sound like a good plan? Okay, and by the way, I think I also forgot to mention about office hours tomorrow. I am basically going to be around all day. And if you want to just come study outside my office, or you think you might have some questions, if you stop by and I'm not there, which is unlikely, probably I've just gone to get a bite to eat and I'll be back soon. I didn't even think I need to put specific hours down. I will be going to dinner right before this session with a friend. So you won't find me from about 5 until 7 tomorrow. But earlier in the day, I should mostly be around. And then also after the review session, I'll be around. So feel free to come by and ask questions. And also on Thursday, when I'm not in this classroom teaching, I'm going to be around just in case you guys have questions for me. Yeah, I'm sorry.
Is the review session in this class?
Oh, I'm sorry. Yeah, no, I found out this room is actually not available. Let's do it right outside of my office, which is in MH33. So yeah, so the review will be down there, and I'll just basically be down there all day tomorrow with a couple of breaks to go outside, basically. Okay. Any other questions for the time being? You've all got the 2 sample midterms. I would try at least one of them. If you try one of them and it doesn't go so hot, I might try the other one. Well, first of all, I might try and study a little bit more, and then I would probably try and do the other one. And then if it doesn't go so well, that might be a cue. Maybe I need to go to the review or something like that. So, just as something else to practice on, I might suggest that as well. But hopefully it's all going well. Even though all of the solutions are posted in Canvas, you're certainly welcome to ask me as well. It doesn't bother me at all. Like, I want to help people. So if there's anything I can help with, guys, do let me know. I'm happy to go over it with you. Okay. Well, let's try and just wrap up this last little bit here that I didn't quite have time to do in my Zoom session last week. I was talking kind of near the end of class about this thing called the crossing number of a graph. And I'm using a notation. This is not really from the book. I just kind of adopted this myself. The crossing number of a graph is just some number. I'm calling it K here. And if you wanted to prove what the crossing number of a graph was, there's really two things that you need to do. One thing is you need to draw your graph with exactly that many crossings. Now that is enough to convince me that the crossing number is no more than whatever that value was. But the critic is going to come and say, well, maybe you just didn't do a good enough job. Maybe I could actually draw it with even less crossings. Now, guys, if there are 0 crossings, right? If you're able to draw it with no crossings, then that's all you need to do to show that the graph is planar, right? But if the crossing number is some value that's bigger than 0, then not only do you need to draw the graph with whatever that sort of optimal number of crossings is, you need to prove that you could not have done better. Even if you tried for 1,000,000 years to redraw this graph, you need to prove that the crossing number could not have been less than K. And that's usually done with a little edge analysis type of thing. So it's a 2-part process usually, unless the graph is actually planar, in which case all you have to do is step 1, draw the planar representation, because obviously step 2 doesn't really apply in that case. Let's do one example together of this, and then I'll see if anybody, I think half of the homework was this process, right? So, but let's just do one example here. What is the crossing number of the Peterson graph? Now, this is not a name that you need to remember. It is a famous graph that I don't think I've used before as an example. What it is you basically have a pentagon on the outside. So you have a little pentagon here. Let me draw this pentagon. And then you have these edges that kind of come in from the side on all 5 vertices here of the pentagon. You create this. And then on the inside, what you do is you make a star. So you draw this as a star like that, and that is the Peterson graph, okay? And the question is asking us to find the crossing number of it. The way it is originally drawn here, you see that we have 1, 2, 3, 4, 5 crossings on the inside. So as it stands right now, this is going to cost $5 million to build these highways with bridges. Each bridge costs $1 million anytime 2 edges cross. So the question is, can we reroute any of these edges to reduce the number of crossings? You see the one that's going like right across the center here? I could pull that edge sort of outside a little bit further. So I'm going to remove this edge. Sorry, I'm going to be erasing a little bit here, guys. And I'm going to try and draw this one like out here, like that. Okay, so I've kind of tried to draw this with a few less crossings like so. So there were 2 crossings there. Now I've only got 1, for example. So I've cut down a little bit on my crossing edges. And I can do that same thing like with another one of these edges. So I could take maybe the edge that's right here, this one right here. And I'm just going to remove that kind of also around the outside a little bit of this other vertex. I'm going to kind of pull that around there like so. And if I do that, how many crossings am I down to? Let's see. I've got 1, 2, 3, right? Those blue crossings. Can we do any better than that? Hard to say for sure, but it doesn't seem like we could do any better than that. So the trouble is if we don't know what the answer is, then we're not sure if this is as good as we could do or not. What we could do is work on the edge analysis as well to see what's going on. So again, let me just redraw, just so we have the original picture back up here again. Here is the original graph. Just drawing it really quickly here, right? So let's just remember some of these edge inequalities that we learned. So one of them was that as long as the graph, so just these are some facts. So number one is, so the facts all assume that G is connected and planar. And there has to be more than one edge, but that's obviously going to be true. Then in this case, then E has to be less than or equal to 3n minus 6. So that would have to be true. And then the second inequality was if G has no 3 cycles, then the number of edges is actually less than or equal to 2n minus 4. So you get a more restrictive bound there. But actually, this graph does not have any 3 cycles. If you try to find a triangle in there, you will not be able to. There's no triangles. But actually, this graph is even better than that. It actually doesn't even have any 4 cycles either. This graph has lots of 5 cycles, right? The star and the pentagon around the outside, but there are actually there's no way to make a 4 cycle here. And there is a third fact, which we are going to look at in group work number 11 in a few minutes. So just to give you a preview of it, I'm going to have you prove this third fact. It works the same as the first 2, so it's just a good review. If G has no 3 cycles and no 4 cycles, then we can get an even better inequality to use, which is that E is less than or equal to, let me grab the formula because I'm suddenly, yeah, it's right here. It's not right here. That's the wrong base. It's 5/3 of, here it is, 5/3 of n minus 10/3. There we go. So in the group work, I'm going to have you guys prove that. It works the same as the proofs of facts 1 and 2, but you just have to make a slight tweak to the argument. So that'll be a good chance to review that. So let's look at this Peterson graph and figure out what is E and what is N in this case. So how many edges do I have in this graph and how many vertices do I have? Let's start with the vertices. How many vertices do I have in this picture?
10.
10, right? There's 5 on the outside and 5 on the inside, so N is 10. And let's calculate the number of edges. What is it? 15, right? Yeah, there's 5 on the pentagon on the outside. There's 5 on the star in the middle. And then there's the 5 spokes that are connecting the star to the pentagon. So there's 15 edges there. So let's just see if let's just start with the first fact at the top here and see what that gives us. So in this case, E was 15 less than or equal to 3 times 10 minus 6 is 24. Okay, well, that's not a contradiction. Okay, so that doesn't help me. That's not a contradiction. Let's try the second one. If we put 15 edges in here, less than or equal to 2n minus 4, 2n would be 20 minus 4 is 16. Well, that's still not a contradiction. It's getting closer, but that one's still not good enough. And so let's go to the third one. The fact that we still haven't proven yet, but we're going to do it in the group work. 15 is less than or equal to, so now I'm putting in n to be 10 again. 50 thirds minus 10 thirds is 40 thirds, which is actually 13 1/3. And that is not true. So what this proves is that this graph is not planar. This graph is not planar because if it was planar and connected, and because there's no 3 cycles and 4 cycles, this would have had to be true. So G is not planar. But it's actually even better than that. If this graph had a crossing number of 1, if there was one crossing in it only, you could remove the edge that was in that crossing, and you'd be left with only 14 edges, but your graph would then become planar. But we know that even with 14 edges, this inequality would be failing, right? Removing this edge is not going to change the assumptions that there are no 3 cycles, 4 cycles, or that it's connected or planar. So actually also crossing number of G is not 1, since removing one edge still gives 14 less than or equal to 13 1/3, and that's a contradiction. Because the graph would have to become planar, right? If you have only one crossing, then you should be able to remove one edge only and create a planar graph. Are you guys following this reasoning? Okay. But now, if I do remove 2 edges, let's say the crossing number was 2. If the crossing number was 2, I could remove the 2 edges that are involved in that crossing, and I would be able to remove both crossings and result in something planar. And if I remove 2 edges, I don't have a contradiction anymore. So at that point, it is possible that this graph could have a crossing number of 2. I could remove the 2 edges and end up with something that is true and is now a planar graph. So actually, I claim that this graph has a crossing number of 2. Okay, so the proof is that the above work shows that the crossing number of G is not 0 or 1. So my little edge analysis here shows that we have to have at least, basically it's this last part here, number 3, right? This shows that your crossing number has to be at least 2. If the crossing number was only 1 or less, you could remove 0 or 1 edges, and this would need to become true, and it doesn't. If I take edges away from 15, if I only take 1 edge away, it's still a false inequality, and so you can't end up with a planar graph by just removing 1 edge. That means there must have been at least 2 crossings, which is kind of what we're saying here. So far, so good? Yeah.
So, like on the homework number, C.
Yeah.
There's no like cycles, no facts, right?
Yeah, you have 3 cycles here, and on part C, you do have the 3 cycles, so you're stuck just living with the first one.
Yeah.
That is true.
Yeah. Would that mean that it's planar then? Or not necessarily?
Not necessarily, you still have to calculate E and N and see if this fails.
Yeah.
If this fails, then your graph's not planar. If it holds,
yeah,
then your graph might be planar, and maybe you can redraw it so that it is planar.
But it doesn't guarantee it, right?
Unless you draw it as a planar representation, it's not guaranteed to be planar. That's right. That's right. Okay, so I claim that the crossing number is 2, but I have a little problem here. I have a drawing over here that still has 3 crossings in it. So does that mean I'm doing it wrong? Possibly. Let me try again. Can I erase? Let me see if I can. I'm going to redraw that picture with only 2 crossings. I think I can do it. Okay. So let's try. I am actually going to leave the pentagon on the outside exactly the same. So I'm not going to move that at all. And I'm actually going to keep the vertices exactly the same on the inside as well, so I'll draw the 5 positions for the vertices on the inside as well. And what I have to do is, this is just not quite making sense to me. I have a little picture here. I'm just trying to understand it. Yeah, so I don't see, there's no reason why I can't just connect these up. I should be able to do that. So far I haven't created any crossings. Now, what's the best that I can do with the center part? So maybe I can go like this and this. So I've got all but 3 edges are now in place. And the question is, can I draw these edges with only creating 2 crossings? Seems a little.
That would, as soon as you go across, it'd make 2 crossings.
Maybe,
Pardon?
As soon as you connect the middle ones, doesn't it make 2 crossings there?
These,
Yeah.
well, I
Oh,
don't
actually,
have
you
to
can
go
go
straight
one. You can go
across.
one. Yeah.
I'm gonna make 1 cross, this is what I
Yeah.
had before. I made 1
Yeah.
crossing like that. The problem is.
That would make another one here.
Can we draw like outside first? Like, instead of being bigger, just have it
Put them on the outside.
Yeah.
I wondered if that might be the way to do it. It's not, I'm trying to understand, I guess my picture might be wrong. Yeah, it would be tempting to try to draw it on the outside. Yeah, so it's obviously at most 3. From the picture we already drew. This one's a little bit tricky because, yeah, in my notes, I am claiming that it's 2. I might have that wrong. I think my picture might be wrong. I'm not sure. Maybe it is actually 3. Somebody want to look this up for me? Grab your phone. I'm just curious, crossing number of the Peterson graph. I'd like to see if that's 2 or 3. I don't seem to be able to draw it with only 2 crossings.
the crossing number says 2.
It says 2.
It is 2.
There's a
Okay, that's
picture.
what I thought. So somehow
Dr. Ennin, there's a picture.
they have a picture of how to do it. I love it. I love it. Oh, you know what? I see. They kind of cheated a little bit. Oh, so they moved this vertex. They did move the vertices around a little bit. So let me start over. Can I borrow this?
Yeah.
I think it's gonna be better than my picture. So let me start over. So I've got this center line here like that. That's fine. We'll keep all of that there. And then the vertex that would have been up here at the top, we can move it down here and draw, that's 1 crossing right there. So that is a crossing that we have. And then this vertex is actually going to connect up to here. This vertex is actually going to connect down to here. And other than that, we're just going to go around the side of this pentagon like that. I think that's the whole picture. Do I have that all filled in? I think that's right. Thanks. That's really good. Yeah, so this top vertex got stretched down to the bottom like that. And also the connections here on the bottom were twisted around. That was kind of clever. So this vertex goes over to this one, and this vertex goes over to this one. So do we actually have the right number of edges here? Every vertex has degree 3. That's consistent with this graph. Remember, we have our handshaking theorem. So if I add up the degrees of all the vertices, it should add up to twice the number of edges. So we have 10 vertices, they all have degree 3. So this is it. So I have just 2 crossings here of my planar graph, of my Peterson graph. So there's one crossing right there, and there's one crossing right there. Very interesting. Okay, so yeah, that's not the way I had it in my notes. So this is a better picture of it. Okay, so now I'm going to change my proof over here. Crossing number is at most 3. Now I can accurately say that it's at most 2. So we proved that the crossing number is 2 by proving that it's not 0, not 1, but it's at most 2 based on that picture. So therefore it's equal to 2. Good enough? Okay. All right, so that's kind of a tricky one. If everybody's okay with that, what I would like to do, sorry. Get out of your way, catching up on everything.
Yeah.
What I would like to do is see whether anybody would like to ask me any questions on the homework that's due tonight. Normally, I don't do homework in class so much for a 400 level class, but because of the exam coming up, I just want to see if anybody's struggling with anything that's due tonight. There are the 4 graphs. So there's these 4 graphs that you have to find the crossing number of. Try to do it basically this analysis, except maybe you can do a little better than I just did. And so the 2 parts that are over there. Some of these are planar though. So if they're planar, you can just draw the planar representation and you're good to go. And then the other part of the homework was there's a couple problems out of the book. So is anybody wanting me to go over any of those problems? Part D, the K3-4. Sure. Let's talk about the K3-4 graph. That's the complete bipartite graph, right?
Yeah.
So the complete bipartite graph, so let's look at K3-4. If I actually just want to draw the K3-4, sort of the way it's put in a standard drawing, you would have 2 camps of vertices, 4 vertices in one camp and 3 in the other, and then you just make all of these edges, right? So you're going to draw all of these edges. There's lots of crossings if I draw it like this. Okay. So this is the way the graph of the K3-4 looks. And how many vertices do we have?
7.
7. And how many edges do we have? You can either do the handshaking theorem, or you could just remember that the number of edges in KMN is m times n. So it's actually going to be 12. Yeah, so there's basically, if you add up the degrees, you have 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4. That's 24, right? Is that right? Yeah, 24 divided by 2 is 12. So you have 12 edges here. Now, it's a bipartite graph, which means that it does not have any 3 cycles in it. But it does have 4 cycles in it. So I'm only going to be able to use fact 2 right now. So fact 2 can be used. And so if K3-4 was, by the way, we know it's not planar, because we even know that K3-3 is not planar. But if this was planar, then the number of edges would need to be less than or equal to 2n minus 4. In this case, that's 12 less than or equal to 2 times 7, which is 14, minus 4, which is 10. So even removing one edge would not give me a planar graph. Because if you take one edge away from this, you're still going to fail this inequality. Okay. So that tells me, so from this, the crossing number of K3-4 is at least 2. I have to remove at least 2 edges to even make this inequality work. And then the trick will be, can you redraw this graph so that it only has 2 crossings, right? Did anybody manage to do it? Does somebody want to do it? Lindsay, do you want to come up and do it? All right, why don't you do it? I'll take a break.
promise someone you did.
Did I do it?
Yeah, when we were downstairs.
Oh, okay, well, that's all right, you can just take credit for it. You can take credit for it. I obviously didn't do very well on the last one, so we need a new teacher.
Oh, that's-
So the trick with these is usually to take the two camps and sort of take one of the camps and move half of the vertices to the other side of the. You see what she's doing? The
Mm.
camp of 3 is in the middle, and what she's doing is she's taking the camp of 4 and putting 2 of them on the top and 2 of them on the bottom. That's like a clever way of like reducing the number of crossings, just pretty clever. Sorry, were you saying something? Chris?
Oh, I just had a general question
Okay.
about the quiz, the second problem. Did you actually want us to find the recurrence relation for that one?
Okay, I have no idea what you're talking about. Would you ask me later?
Yeah.
Yeah, I'm not sure what you're talking about. Let's see if we're getting this. Oh, I think on part B of that quiz question, no, not on the, you're talking about the actual quiz.
Oh, because the review you mentioned. I just wasn't sure if we could just plug in Chuck or it was just a general. Like,
I better let you ask me later. I'm not
Yeah,
quite
yeah.
sure I'm understanding. Okay. All right, so Lindsay's got a good picture there. There's 2 crossings. She's circled them for us. And the 3 vertices, great. Thank you so much, by the way. The 3 vertices in the middle are exactly these 3 vertices. And then she's just taken 2 of them from the top and kept them on the top and 2 others of them and moved them to the bottom, right? And actually, but something is wrong because every vertex has to have degree 3. I think you mean to have
Oh,
this
yeah,
one
there's
here.
one coming, yeah.
Yeah, there we go. And other than that, I think we're good. Every vertex should have degree 4 on the middle row, and all of the vertices should have degree 3 on the top and on the bottom. So that does work.
Mm.
Everybody comfortable with that? So this picture, so from the picture, the crossing number of K, 3, 4 is at most 2. So it's at least 2, now it is at most 2, and so therefore it's equal to 2. Good, I like it. So keep that in mind with the complete bipartite graphs, that you can take the 2 camps and half of the vertices can be kind of flipped to the other side of the other camp, and it just reduces the number of crossings tremendously. Awesome. Any other questions on the homework for tonight that we could do together? Yeah, Alyssa?
You can go over 26.
From the book, actually. Let me grab my book and let me see what we can do with 26. It's in chapter 12, right? Okay, so let's look at number 26. Ah, yes. Actually, let's do 26. I think I'll just do it right over here, maybe. Okay, so grab my camera. 26 is saying, so on 26, G is a planar graph of order n. And every vertex has degree K. And the question is basically asking us to prove that K is at most 5. This is going to be the idea here. Okay. So let's see how we could do that. I would start with the handshaking theorem, right? So if you add up, so for the solution, by the handshaking theorem, which is certainly a big result we've learned, if we add up the degrees of all of the vertices, it's supposed to be twice the number of edges. And the degree of every vertex is k. And the number of vertices is n. So what you have here is actually nk, right? Equals 2e at this stage. That's what we're going to have so far. All of this has nothing to do with the graph being planar. So how do we use the fact that the graph is planar to help us now? I'm sorry? Okay, from the first fact, okay, so I guess did it say that the graph was connected? If I want to use the fact, technically the graph should be connected. It probably should.
I think I assumed.
You just assumed it. Yeah, let's just assume whatever we want. Sorry?
Can you assume it for every connected?
Yeah, you could just do this for every connected component. So you could just say, I'm going to, even if the graph is not connected, I can just do the proof on a connected component. So it actually is fair to assume, so we may assume G is connected. I'll just say by restricting to a connected component. See, each connected component is still going to be planar, is still going to have every vertex of the same degree. And so by fact one, the number of edges is less than or equal to 3n minus 6, right? So we have that for sure. Okay, and so actually what we could do is feed that inequality in where we have e here. So this is now going to be less than or equal to double of what this says. So e is less than or equal to 3n minus 6. So 2e would be less than or equal to 6n minus 12. Does that look okay? Okay, and now if I just take this nk less than or equal to 6n minus 12, I can just divide through by n. And thus, if I divide through by n, k is less than or equal to 6 minus 12 over n. But this is some number that's less than 6, but k has to be an integer. So that means that k is actually less than or equal to 5. It could not be equal to 6. So it would be at most 5 at that point. And that would do it. Yeah, Alyssa?
So like you don't have to go into like cases of like the different ends, like different numbers of ends.
Of ends?
Yeah, like vertices.
Of these different values, I don't think so. I actually don't think there's anything in this proof that is forcing us to make assumptions about n. It's a very arbitrary value actually. So it's a short proof actually.
But like trivial cases, doesn't fact one assume like n is 3? Because the other cases are pretty trivial.
If n was only 2,
Could be 0.
well, first of all, every graph, yeah, if n was only 2, every graph is going to be planar. These are the only 2 graphs of order 2 that you have.
Yeah.
So I'm not really sure that would be terribly interesting. The degrees of the vertices here is obviously less than or equal to 5 for both of
Yeah.
those pictures. So it's
So I'm
really,
wondering for fact one, if we can just say n is greater than or equal to 3 to make it more interesting, because the other ones are trivial, not very interesting.
sure. Yeah, I think you could do that. I mean, if n was equal to 2, actually, it's not that it's trivial. It's really then in that case,
Yeah, it's
e is less than or equal to 0.
0. Yeah.
Right, which is
Which is
not going to be true
Yeah.
unless
It's not
there's no
true.
edges.
Yeah.
Yeah, so that's a good point. Yeah. So let's see.
You just mind going over how we got NK again?
Yeah, you're adding up all these numbers. Every single one of those numbers is k. So it's just k plus k plus k plus k. How many times? However many vertices there are, that's n. So you just get n factors of k. Yeah. Sweet. Anything else that we should talk about here, guys? If anybody wants to check their answers with me later on these crossing numbers of these other graphs, feel free to do that. I can just tell you what the answers are and just make sure you've got the right things there. But I think that should be, pretty good. There's only a couple of other problems for you to work on. I'll be around after class. If you've got more questions. I think that should be okay. What I would like to do, guys, is I'm gonna pass out this group work. Except that I have actually done most of this group work already for you in the various Zoom class we had last week and so on and so forth. So on this group work, let me just put it over here so it doesn't get lost. This is group work number 11. I'm only gonna ask you to do a couple of things. I want you to try and do problem 1B, which is actually fact 3 from this list over here. And then if you get done with that, you could try problem 2B. As I think I've already done 1A and 2A for you in the past. So let me send this around. Some copies of this handout here. 4. All right, and 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4. And just do what you can, grab 2 or 3 people and you guys can come up and use these whiteboards all you like. But focus on problem 1B and problem 2B. And see what you can do. I'll get this erased.
That's what we learned about the friends to be how to use it.
Okay, get out of your way here. Come on down, guys. Guess let's do that later, okay?
The notes.
Oh, yeah, you can use the notes. Oh, okay, for the group. Oh, yeah, that's fine. I thought you were doing.
No.
Let's see. You guys aren't gonna make any mistakes, right? Of course not. Everything will be perfect for the internet.
That's green and which one?
So then you can let it, you can just correct them as they go along. That's right.
That's the other one. Did you see her? That's really close it. I said.
I don't think so.
That's right.
Because every region has a four edges around it. There's no three cycles. If there's no three cycles, then they have to at least four days.
I think it's just this one that's in it. It has to be at least two. Okay.
Exactly. So you just gonna basically take that.
He said, bigger than or equal to 4 bar.
Great, great, great.
And the other one, it was 3.
Okay, so does that mean
So it should be 5 RMs, I believe so.
at least? And then there's no 4 cycles.
Yeah, we have no triangles and we have no quadrilaterals in the graph. There's no 3 cycles and no 4 cycles. Every region will have a degree at least 5. Does that make sense? That's the only change in the proof from what's already in your notes. And you should definitely know this proof. Because we've seen it many times. Is it basically you're just putting this number is always one more than the last one that you left off with in the assumptions. Okay, so far so good. That looks good. When your hand gets tired, Hamza, you can just pass that marker along, let someone else jump in and help you. Okay.
I reckon.
Okay.
They're bounded by the. There's one of the 5.
Oh.
Oh.
Yeah.
Find from this, which is why it's like. It's three. It's all right?
And that, no, time.
So I say, he sort of just goes with the inequality. Like,
There's also no.
he says this is less than or
We
equal
don't
to.
have any quadrilaterals.
So like, what does he substitute?
And those.
He gets, he solves this property on, so like, two E, yeah.
This
So
sells
those
us
numbers that you're adding up there and
Like,
then.
just divide both sides
Every
by.
one of those is at least five. But it's at least five, so it's like you have five, plus five, plus five.
He is.
So like at the very least.
Well, he eliminates, so he goes from this step to this step and he gets rid of the R.
Could be more than that.
So you have to write, sort of R in terms of
Exactly.
E. So you divide by five.
I to divide R, it's not necessarily pretty.
Oh,
Yeah, divide both sides.
Could be.
That's all I was told this, like, it could be, but.
Okay, so then
Uh-huh.
two equals R E.
Now that is a five
plus
side.
10.
And that would have a degree
R minus
of
E.
five.
Yeah, but if you don't have five. we could-
Well, R by itself, not E.
But it does,
There's a
balance the
possibility into how you represent R.
The point is, none of those numbers that you're adding up are threes. That's, you have no three cycles, you have no four cycles.
And then that would equal
Nothing over degree
to
three or.
Oh.
So you're adding up a bunch of numbers. that are all
two E
five.
five, so minus
What's the
five.
lowest they could add up to? That would be if they were all
Negative
five,
3.
and you have R in any of those values. So five is part of like the smallest. degree.
Okay, so then therefore 2 is less than or equal to that, and then that is.
I'm glad we're practicing it then. Glad we're practicing it. Okay, sounds good. Does anybody need a hand?
Oh, that's.
Needs to work? That's true. Yeah. So every one of these numbers is.
So from this and that and that. and 2 is like-
Oh, this formula that she's got that exact. Plug that in there. It's. Yeah.
So now we just solve for E.
Anything working out over here?
And so we move the stuff over, I guess.
Oh, yeah.
Fitting pretty close.
And then you multiply with the divide.
Yes.
The most like they have spot.
Yeah.
And you have
And
Sorry,
the smallest amount of edges.
And then when you divide by negative five. Yeah. Yeah, okay, that's what you wanted.
I literally just do it.
That's how it works. So if I gave you a problem Thursday, they said there's no 3 seconds, no 4 seconds, and no 5 cycles.
Oh, so
You got to a 6, and you do this first again. So this is one that's worth kind of understanding how it works. We do these inequality on some of our examples.
So.
Yeah, that looks great.
I would say that this.
Guys, you feel pretty good about this?
we basically solve for R.
Does this look okay? Yeah, that does look good. So if I ask you a question on Thursday, that there's a graph that's planar that has no 3 cycles, no 4 cycles, and no 5 cycles. You know how to edit this proof, just tweak it so it could give you a new proof for a new inequality.
This is, so we can move this guy over.
Jack that up to whatever the next number is, which would be a 6, and run through it again. That's right. Of course, the more of those assumptions you put on it, the less graphs are actually out there that you could use the fact for. It's kind of nice to get these better and better inequality. At least we could use it for the Peterson graph today. But as the graphs get bigger and bigger, and there's no 3 cycles, 4 cycles, 5 cycles, and so on, there's going to be less graphs that you can actually use the inequality for. So there's always pros and cons of everything. This is the best inequality you see yet for getting contradictions, but it can only be used on less and less and less graphs, because your graph has to have none of those cycles. Okay.
Oh, right.
All right. Does this?
Yeah. The other one's like.
This is kind of, I would call it the handshaking therapy for regions. Yeah, it doesn't really have a name, but it is also kind of like a handshaking therapy.
Yes.
Yeah, absolutely. Absolutely. Robert, jump on in here, bud. All right, great. So that's, 1B. See if you can do 2.
He said that.
Okay, let's see how it is.
This truck we got here is just right.
From the Oilers.
Okay.
Okay, so.
What I read. He said every region has a degree of at if your edges are over
Crossing number of cases.
then look at the next sign. Anytime you have more than edges.
Oh, wait, that's not-
You're doing like a hard side or something?
It was if this happens.
It looks more like this, and you're not even doing it. Yeah, that looks like that's what we're talking
It's
about.
not too bad.
Yeah, be careful.
That's a upgrade.
Everybody good with this?
Making sense.
And that's true, right? I'm not telling them a lie.
Yes, that is true. The only way a region would have a degree 2, well, you could have a degree 2 region if it was just that. Then this outside, there's only one region in this double counts. But other than that, if there's more than one edge, yeah. We know there's at least 2. We know that if we were under the edge, it's not using multi, let's not line for this. So you can't say, oh, well, here's 2 edges. Right, and I've only got a degree 2 region. Graph, that's a mobile.
How about that's 6 versus all points.
Everybody's connected, everybody, yeah.
I was thinking, I was like, that's right.
I think that's.
Oh, on Thursday, if I ask you to do an edge inequality for a graph that has no 3 cycles, no 4 cycles, and no 5 cycles. Change it to 6, run the math, get a new inequality. That's exactly right. Exactly. So this is a good proof to make sure you kind of understand complex.
But that's
Great. For part A, now that's easy.
I think I know the video.
Oh, yeah, everyone else. Oh, yeah.
Yeah.
No, but I guess if I have it too.
I'm hoping you wrote it wrong. One of us wrote it wrong. Let's put it that way. That's the only theorem I know.
Now it makes sense, like, why is this one data this?
Yeah.
I like to eat on. I don't really need our.
Oh, yeah, you're right.
It's better if you wrote it wrong, because then it's not everybody in the class lost, it's just your notes.
3 and minus 6
I think you
would
did
be.
all your pictures.
Did I?
Yeah,
Times 3 is 18 minus 6.
Well,
Oh, is this one? I think you.
Oh, so E would have to be less than or equal to 12 for it to be planar.
You had.
And so you can remove up to.
yeah, it needs to be, just draw a cleaner.
I didn't draw this.
Like directly on the recap. Then we-
Oh,
we-
done.
we would have to do, let's see, fix that out. I was like, yeah, I think
I
I
wasn't even thinking about that. All right, somebody's got to help Marcus out. Okay. Good so far, guys. I like it.
Looks to me 15 less or equal to 12.
We did A and notes. Okay, following. One B is the one that we had to do, because 1A we did.
2 edges, right?
2 edges.
Yeah.
Oh, you're talking about 2A?
Oh, yeah.
It still won't be planar. So what does that prove about your crossing though?
Guys, there's a delta in your son.
At least,
Yeah, these
I think it's at least, he says if we move up to 2 edges, it's still not planar. So the crossing number would have to be at least 3, at least 3, right? So the number you put there is always the difference. It's like how far the inequality fails by, in this case, 3, 15 versus 20. So the crossing number is at least 3. So I would like you to pass the marker to any other person who hasn't done it yet and help coach them through how to try to draw that graph with 3 crossings. It is actually, that is the right answer. It is going to be 3. So we just have to figure out how to draw it. Okay? Let's see how we're doing here.
Yeah, that's why.
Yours next, that's here, it's gonna take us a little. Good alignment.
And that's it.
I would say case like 4 p.m.
Probably just say the removal of 2 inches. Still not. Oh, I see what you're saying. If the crossing number is less than 3, then graph. That's so that just top 5. And I mean, it's just coming out of each spot. So try to see if these guys are all working. Draw this hexagon. Okay. Somebody's working on the edge analysis as well. Somebody could be working on that. Okay. I'm working on the edge analysis, so you kind of know. Oh, look at this.
We don't-
This one's so these 3. How much? So that's. That's really good. It's really good.
Yeah.
Really good.
Oh, we know it's good.
Okay.
No, it's not.
That one extended to feedback, and we're like 6 15 guys. That's the.
When they
Okay,
I think these 2 with only making 1 crossing. Just go.
Oh, yeah.
Kind of
Oh,
a
I thought someone.
skirt around the outside of that vertex. Andrew? Go from here over to here, but draw it around this way. There you go. So you made a crossing here. You've already got one here.
They should also have 1, 2, 3, 4, 5.
And you need one more edge here to go to here, right? Can you do it with only 1 crossing?
Oh, wait.
And do we have all the edges now? Every vertex should have degree 5.
Wait. Oh, yeah.
So you've done it. This is the whole graph. You've got 3 crossings. No, you can't do better than that. So that is optimal. What do you guys think? Make sense? All right. I like it. Good job, guys. Excellent. Excellent. Is everybody getting this? The crossing number should be 3 on that K6 graph. Oh, yeah. 3 crossings. Yes. If you remove the less than you would not be able to. The argument. He's gonna draw it with 3 crossing. It might be the hard part. It depends on your point of view. No, it just takes. We just don't have it.
What's this? And then.
Yeah.
That already. Start with
Oh, yeah, we need better markers. I got better markers. Also, make sure every vertex has that.
Funny.
because it's case. So that's one way to make sure it's actually got.
It's funny because that proof you can draw in the notes.
Yeah. They're just thinking about.
Oh, should we actually just here?
Never a good idea.
Yeah.
How that works.
Are you feeling better? No, yes.
Yeah, yeah.
He's going to Long Beach for grad school.
Wait a minute.
He is. Oh.
Yeah.
Well, you couldn't get in anywhere better.
That's gonna keep us in. So.
It's, I mean, it's not like out of this world good, but it's not bad. There's definitely good people there. What does he want to do?
Oh.
Because if he wants to do like algebra, we have some really good people.
I think he does land.
Okay, then it's like a go-to program. Don't go there for topology, geometry.
Sometimes the direct path is the best way.
Analysis, yeah, it's fine. You can, there's especially some very good analysts. Yeah, if you want to do algebra,
But
or
he
like,
said so bad.
no, because it's terrible for like geometry or topology, which is the stuff that I want to do. Yeah. We only have like one person that does topology and like two people that do geometry, but they're really hard to talk to.
You guys trying that one again?
I'm just trying the first one. I was like a little confused when he did it, so I'm just trying to do it.
Good idea, good idea. Coaching from your team. Did you get it?
Yeah.
Okay. And you make sure you double check. That's the key. You. Great. Nice job. Nice job. You guys have trouble with the graphic? It's It's possible to draw only 3 crossings.
Okay, now let's count. Okay.
Yeah, make that big outside.
So it's.
Yeah, there you go. We did it.
Yeah, that's if it's connected to plane.
That looks great. Just don't
Yeah.
erase it.
Okay.
So, there's some groups that have. Yeah, that does look good.
And also there's that handshaking theorem for regions.
That is.
Two R. Sorry, 2E.
This is 2.
That's 2E.
Yeah.
Oh, wait, did
Yeah.
The ball.
Has to be.
And so if it's planar,
Is that less than or equal to variant? Or is it equal?
it's equal.
Okay.
Yeah, I think so.
No, I mean to the region.
Hey, guys,
Oh, the
I think some of the groups have managed to draw this K6 with only 3 crossings. And others are still working on it, but I'd like to kind of wrap this up because I've only got about 10 minutes. If you want, Lindsay and Jean have a wonderful picture back here of it, as do Ashley,
Proof of it
Marion,
from the
and
note.
Vivian up here in the front. So grab your phones. They've given me permission, I hope. To let you like
where's the
steal their picture.
Oh,
there's no 3 seconds, so it has to be
Solutions.
greater
So
than
you
equal to
might want
4
to just
R.
take a quick photo with your phone. And then.
And then that solves it, yeah.
Okay, that's the part I
Don't
Yeah,
worry
yeah.
about it too much, like if you've been trying to get it and you're like, I can't draw it with, I can't get it to work with only 3 crossings. You know, this just takes a little bit of practice to get the hang of it, and it is possible that you can totally understand the material, but then struggle to draw the graph. That is for sure a possibility. But I actually want to bring us back together. Because there's one last thing I think I've alluded to, but I have not formally discussed it yet. So, yeah, this is interesting. So they actually drew the last vertex in the center and kind of made it into a pentagon. Kind of interesting idea. Yeah, I like that. I like that. Okay. There is one last thing I want to go over, and this hasn't really shown up in the homework, but it's actually a big result, so I do want you to be aware of it. And it is something called Kuratowski's theorem. So let me just write this down. Kuratowski's theorem. So we'll just take a few notes here we only have like 10 minutes. I just want to get these last notes in there. And what it says is that a graph is non-planar if and only if. So this is a theorem that is really a characterization of non-planar graphs. So unlike the topic of Hamilton cycles, where we never came up with a nice if and only if characterization of it, here we do have one. We actually have one. And what it says is that a graph is non-planar if and only if it contains a subgraph that is, and now I'm going to use a word that I will have to define in a minute. And the word is homeomorphic. It contains a subgraph that is homeomorphic to K33 or K5. This is Kuratowski's theorem. Now, we already know that any graph that has K5, we already know that K5 is not planar. We already know that K33 is not planar. I showed that in the video that you watched, which used some of those edge inequality facts. So both of these graphs are not planar. And if they were to occur as subgraphs of something else, then the larger graph that contains them as a subgraph is also not planar. So like K34, which is from the homework, is not planar. K6 that we just did in the group work is not planar. And that's partially because they contain these subgraphs, which are already not planar. If I can't even draw the subgraph without having edges crossing, then of course the bigger graph is going to be even harder to do. I wouldn't be able to do that even. Okay. So if I didn't have the word homeomorphic here, everybody would be happy. A graph is not planar if and only if there's a subgraph that's K33 or K5, right? So I just need to explain this word homeomorphic, and then I think everybody will be happy. It's actually not that big of a deal. So I need a quick couple of definitions. I just want to write this down. Again, there's not really any homework on this, but just a couple of basic ideas. I'm going to start by defining something called an elementary subdivision. An elementary subdivision is just it's a simple concept. I'll show you in a second what it is. This is obtained. An elementary subdivision is obtained by taking an edge. By taking an edge, I'm going to call my edge maybe XY. So that's in braces there. This is my notation for an edge. I've got two vertices connected by an edge. And placing a new vertex. I'm going to call this new vertex Z along the edge. Okay, along that edge in order to replace XY with the edge XZ and the edge ZY. So it's a fair bit of words there. So let me erase here for a second while you guys kind of digest that for a second. Guys, it's exactly what the words are saying. If I have an edge from X to Y, an elementary subdivision of that edge simply puts a vertex on that edge. And now we no longer have the edge XY. We have two other edges instead. The edge from X to Z and the edge from Z to Y. That's just what this says. So an elementary subdivision, if you want to say it in real simple terms, you're just putting another vertex on the edge somewhere. Okay. Right. And so then just the next definition that we need, and this is the last thing, is that two graphs, G1 and G2, two graphs, G1 and G2, are homeomorphic. They are homeomorphic to each other, basically, if we can get from one to the other by a series of elementary subdivisions. That's all. So two graphs are homeomorphic if we can get from one to the other by a series of subdivisions. Let me just show you an example, and I think this will be totally clear. Let me make my first graph just be the graph K5. So I'll just go ahead and draw K5 here for you guys. You guys, of course, know about this graph pretty easily. That's K5. And what I'm going to do over here right next to it is I'm going to draw another graph that is homeomorphic to K5. Since that's, after all, part of what the Kuratowski theorem is about, is graphs that are homeomorphic to K5. So I'm going to redraw the K5 here, guys. Again. But now what I'm going to do is I'm going to do a bunch of elementary subdivisions of K5. Remember, doing an elementary subdivision just means putting vertices on those edges. So here is a graph that I could have. The graph I'm drawing right now is homeomorphic to K5. I have just added a bunch of vertices. Every time I added those dots, I kind of did it arbitrarily. It doesn't even matter where exactly I did it. But every time I added another dot along an edge, I basically split that edge into two shorter edges, which is what this elementary subdivision thing is. And so this graph is homeomorphic to K5. And I think you guys would all agree that if I cannot draw this graph such that it's planar, then putting a bunch of dots on the edges does not change that, does it? Right? It basically doesn't change the essence of the fact that you are still stuck with more or less the same edges that you're trying to untangle. Right? It's just now you've got a bunch of vertices kind of globbed onto those edges. But it doesn't actually fundamentally change the nature of the graph from the perspective of being planar or not. So that's all that there is to this concept of homeomorphic. So any graph that is not planar should have a subgraph that either looks like either a K5 or maybe a homeomorphic version of K5 or K33. So we could do the same thing with K33, right? You know that K33 is not planar by the edge analysis that we had done earlier. And all I'm saying now is, well, if I add some dots onto these edges, that is not going to suddenly make it become planar. Right? Because actually the dots don't matter if you think about it, right? When you're trying to like redraw this graph without any crossing, those dots are like just glued onto the edges, but they're not affecting whether the edges cross each other or not. So it makes sense that this would be possible, but isn't this an incredibly strong theorem? Because it's basically saying, look, every graph that fails to be planar is gonna be because it has K3 inside of it or K5 inside of it. And one of the problems that I did not do in yesterday's review session, which I am gonna do tomorrow night, we're actually going to prove that a graph is not planar by noticing that there are subgraphs in them that look like these. So you can use that as another justification. More commonly, we are using these edge inequalities, right? This kind of stuff. This is how we often show that graphs aren't planar. But I have another alternative now, which is if you can just convince me that your graph has a K3 in it or a K5 in it, then you can use that as a reason. Forget doing the edges and the vertices. Just make that observation, Kuratowski's theorem, and you're good to go. We're not going to prove this theorem. Way too deep for that. And I have like -1 minute left. So I'm not going to be able to do that. Did somebody have a hand up though? Yes, Kyle?
To show that K5's in it, would you have to draw it, or would it be like enough to like state like?
You could just state which vertices they were. Oh, these 5 vertices are forming K5, and it should be possible to just look at your picture and see that every edge is there.
So if you have like 5 vertices, we think of 5 and automatically assume.
Well, 5 vertices of degree 4 in K5, right? But they would have to be all connected to each other. If I've got a graph with 20 vertices, right? You may not have any vertex of degree 4, right, in that graph. So just be a little, or you might have several vertices of degree 4, but they're not like all connected to each other. So you gotta be a little bit careful with that. Yeah. Okay, guys, that's all I've got. Real quick, because
After we read, it would be part of Kuratowski's theorem, right?
right, the only ones that don't apply to Kuratowski's theorem would be K of 2n. And actually, all of those are planar. Do you know why?
Shift 1.
Here's your n vertices. Your other camp has 2, put them on the opposite sides. That same trick we did earlier. You won't have any crossing edges. Isn't that clever? Okay, I gotta stop. You guys have places to go, people to see, things to do. I'll be down in my office. If anybody wants to ask me any more questions, feel free to stop by and I'll be glad to give you a hand. Study well, and I'll see you on Thursday, if not before.
Oh, a little bit more context.